So we're working on this improper integrals. I'm going to bring this in notability, though. So we're going to kind of work with now improper integrals again, but we're going to work with the discontinuity. So these are kind of thought of as type 2 integrals where, for example, you have like a vertical asymptote at an endpoint. Okay, so now you're going to go back to integrals that look like this. Okay, so you're going to have an integral now from a to b. There is no what? You don't have infinity anymore. But what makes this improper here is that your interval now is finite, okay? So this means we have a less than or equal to x less than or equal to b. So I'm going to say, let's note, this is called a type 2. Type 2 improper integrals. And this is where we have a discontinuity. In all honesty, a vertical what? Asymptote. You can have a vertical asymptote in, at a point C, which will be in your interval AB. Okay, so your function is going to be, it's not continuous over the interval. So this has a discontinuity there. Vertical asymptote, really. And it's discontinuous for some point C in your interval AB. Okay? This is going to be a type 2 improper integral. All right? Now, so you can kind of do like an example here. Very simple example. It'd be 1 over x squared dx. So notice this, the function here, you have a problem. Is that right? What's the problem? X can't be 0. You have a vertical asymptote. So in terms of your graph, by the way, here's the graph of the function. And what I'm saying is you're going to try to integrate now between this x is 1 and over here x is what? X equals 0 here. And you try to find this area under the curve. You guys with me on that? So the real issue is the fact that over here you got a vertical asymptote over that interval from 0 to 1. So you go, okay, 0 to 1 here. Oh, we got a problem here, ladies and gentlemen. So you have a discontinuity at 0, meaning a vertical asymptote. So for that interval, you go, okay, I'm trying to integrate this. I'm going to write it down this way. 0 to 1, that's where the issue is. You have discontinuity. So, okay, that's what we call at the left endpoint. So you say, okay, what happens here? What do we do now? Right? Because in general, you got AB. This is at the left endpoint. So you might say, what's the fix? Well, we're going to fix this situation here. You see this imaginary line? I'm going to call that t here, okay? Let's see if we can see this here. I'm going to define an integral I of t now. And now that integral is going to look like this. I'll say this is what we're going to do. You integrate not 0, but what? Let's do that in purple. Yeah. The lower, now this is going to be like an interval to t here, okay? So this I of t, as you guys can see, will be t to 1 over x squared dx. And then as you guys know here, after that, what are you going to do with that t? After that now, you're going to let t now go to 0 from what direction? From the right. Okay, because you're going to approach this t now from the right. So in other words, i.e., here's how that improper integral looks really. That's going to equal the limit t goes to 0 from the right, t to 1 over x squared dx. Now, I'll give you, a definition if I can get this here. We got to do a dx. Okay? So that's the work we're going to have to do, just so you guys know. So like before, this time you're just going to integrate. Okay? This is my I of t. And I'll get my integral here in terms of t. So that'll be, okay, we're really integrating t to 1 x to the minus 2 dx. Okay, which will be negative 1 over x. Is that right? 1 to t. Which is negative 1 over 1 minus negative 1 over t, which is really 1 over t minus 1. So here's my I of t. Double check. Is this right? You guys okay with that? Okay, you guys okay with this one? So far, so good. Now, let me ask you guys this question here. Now, what you do is the what? You have to apply the limit now. Because remember, you found just I of t. It's just this right here. So we now have to let that t value, whichever one you want to look at, doesn't matter. You let that t value go to what? Go to the 0 from the right now. So this is approaching, this is t. It's approaching what? No, not infinity, 0. But t is approaching 0 from the what? From the right. Okay, because you are, the problem here is you have a discontinuity here. It's called a left endpoint discontinuity. It's a vertical asymptote. Because in calculus, you can't integrate over vertical asymptotes. The function has to be continuous over an interval. So what we're doing now is say, okay, let's let it be continuous. It is from t to 1. Okay, this is now t to 1. Now you can integrate. It's nice and continuous there. So you get I of t now. Now let t go to 0 from the right now. And this is going to be, this is now what we have to do. So you say, okay, as t goes to 0 from the right, we want to know, where does I of t go to? So this becomes a limit question. T goes to 0 from the right of 1 over t minus 1. Do you guys know where this goes to? What does this limit equal? Is that infinity? What do you guys think? Is that infinity? I think so. Why is that infinity? Well, yeah. Yes, exactly. In other words, there's a couple of ways we can do this. This is the curve. If this is t, this is 1 over t. You're going to 0 from the right. So in other words, 1 over t gets what? Big. Is that right? And as t goes to 0 from the right, 1 over t gets very big. Something very big minus 1 is still very big. And that's that limit. Now, sometimes people, I got to say this to you guys numerically. T going to 0 from the right means t is positive, okay? And t is getting very small. Is that right? So you can think of t as a small number, like 1 over whatever, 10,000, okay? What's the reciprocal if I said that 1 over t is 1 over 1 over that very small number? Well, doing the arithmetic makes that very what? 1, 2, 3, 4. 1, 2, 3. Here's what I'm saying. That arithmetic, this is the t. That's getting bigger. So the smaller t gets, the bigger 1 over t gets. Does that make some sense? And so this is big minus 1. This is big. Here's what I'm saying. We've shown that this area here is actually, this blows up. This is infinity. So this integral diverges. Now, this is what I have here as a left endpoint discontinuity, 1 over x squared. In the notes, oh, it's still here. Just starting off with that example, where is it? Yeah. It's right here. Left endpoint. I called it case 2, but whatever. Function is discontinuous at the left endpoint. This here is the definition you guys use for left endpoint discontinuity. Okay, because what they're saying here is A is discontinuous. So this is how you define it. Let t, replace A with t when you have that left endpoint discontinuity over the interval. Replace the lower limit with t and let t go to A from the right. But that was the picture. And now you can integrate. And again, if this equals infinity, we say divergence. In this case, it did. If it's finite, we say convergence. So those are my notes. I guess I started with case 2. So, okay. Improper integrals. There we go. That's when you have a discontinuity on the left side. And that's that, okay? Compare that to this example. You say, okay, what example? Now we're going to integrate from 0 to 1 here. 1 over the square root 1 minus x squared dx. Now here's my function here. This is not an improper integral where there's infinity, right? You don't have the infinite intervals. You have a discontinuity at an endpoint. You say, what am I integrating this function here? My function is integrating between the interval of 0 to 1 here. Do you guys know where the discontinuity is now? Yeah, x equals 1 is the problem here, ladies and gentlemen. X cannot be 1 because your denominator can never be 0. So what I'm going to say here is that interval here, you have a discontinuity. This is called a right endpoint discontinuity. you have a vertical asymptote at x equals 1. So just for example, I'm just going to kind of sketch the idea here, okay? I'm not going to graph this graph here, but to kind of share with you guys how that really looks here, okay? That we have at 1 a vertical asymptote. So I don't really know how this curve looks, but I don't have to. But here's kind of the idea. I don't know. Maybe it looks something like this. I have no idea. All I know is around 1, I can't what? I have a vertical asymptote around 1. We have a discontinuity. Okay? So it's a very simple fix. The fix is this. We're now going to integrate here from 0 to what? T. This is my I of t, area under the curve. We're going to integrate now from 0 to t. Okay, so we say, okay, let's integrate instead from 0 to t, the function here. This is that I of t, so you guys know. Okay? But once you get that answer, what are you going to do with the limit part? T, you're gonna do this. You're gonna let t go to what? 1, not from the right, from the left, and you want to see where I of t goes to. I of t goes to. So that improper integral now is going to really look like this. You say, oh, is that the limit? T goes to 1 from the left of I of t? Yes. And what that'll do is, you take that area from 0 to t, get that I of t integral, and that'll approach 1 from the left, though. Because this is now what you're going to get a hold of that variable t here. T is going to go to 1 from the left. Now, that's called a right endpoint, what? Discontinuity. So if I go back to my handout, I actually started with the right endpoint discontinuity when I wrote it. Oh, here's a what? Right endpoint discontinuity. It's discontinuous to the right here. There's the problem. So you say, how do they define that integral? Well, we just did it. Now, the problem is b. Replace it with a t and let t go to b from the left. Just like we just wrote down, just like that. So, you have those two situations, really. So, all together, you go, okay, what is this? This is going to be the limit. T goes to 1 from the left. And now we're going to integrate again from what? 0 to t now. 1 over square root 1 minus x squared dx. That is your I of t in purple. Okay, now the good news is, what's the good news? Do you guys know? Well, it's a trig formula. Inverse sine 0 to t. You guys recognize that as the inverse sine function? So some of those you want to know. You want to know those very well. Now, that now means I got inverse sine of what? T minus inverse sine of 0. Now, what's inverse sine of 0 going to be? 0. So you get inverse sine of t. So this becomes now, again, now it's a notation thing. You can say, okay, as t goes to 1 from the left, where does I of t go to? Or you can just say this is really the limit now of what? t goes from 1 from the left, inverse sine t. Does anybody know what that is? Do you guys know? I think it's continuous at 1. Is that true? This is continuous at 1. What's inverse sine of 1? You might say, okay, inverse sine of 1. You guys remember that? This is like that trig, the trig video I showed with you guys. In trig, they're going to do that. You let theta be what? Inverse sine of 1. That means sine theta equals 1. What does that mean about your theta? What does theta have to be? Pi over 2. Yep. So this limit is really going to be what? Pi over 2. Since the limit is pi over 2 now, this is from trigonometry. This is when I shared with you guys that video. Hopefully you guys took a look at that. Because there's trig in calculus 2 and trig in calculus 3. So you guys want to look at that. So this is pi over 2. What does that even mean, though? You guys know what this means? That this area equals what? Pi over 2. That means your integral, what? Converges. Because that number is a finite. That's a finite number, less than infinity. Converges. So you can actually take the area. This is wild, ladies and gentlemen. This is really wild. Why is that thing wild? Because in calculus 1, you integrated, let's look at that curve. Where's Desmos? Right? See this curve? This is the curve, by the way. Let's say x equals 0. X equals 1. And I kind of like just coloring these here red. Anyway, did I do it? Okay. Here's my point. If I can, I might be able to fix it a little bit, just kind of just to. Guys, see what I'm saying? That's the curve. But I want to remark about convergence and divergence, just so you guys know. This question, the area under the curve for this question is finite. Even though you have a discontinuity on the right at 1, you have a vertical asymptote over that interval. So calculus 1, you get to integrate over a nice continuous function over an interval, closed bounded interval. Now you go, what if you have this vertical asymptote? It's not continuous at an endpoint. That area is still finite. Now the reason in this example only, there's others, but sometimes it'll be finite, sometimes it'll be infinite. The reason it's actually, I would say to you guys, finite is because the curve gets close to the x-axis, the vertical asymptote on the right, very fast. That's why. If you said, what about the other situation you gave us? The first example. Y is 1 divided by x to the second power. Okay? Get rid of this. Change this color. And wasn't the other one 1 to 0 too? Here's what I'm saying. Your vertical asymptote, ladies and gentlemen, is at x is 0. Do you guys see that blue curve getting close to the vertical asymptote quick? The answer is what? Not really. It's too slow. So that curve gets close to the x asymptote a little bit too slow. I like this picture better. This shows it maybe a little bit better. You see the blue curve in the first example? You're getting too slow it's too slow getting to that vertical asymptote. So that's really what's happening if you guys want to know the truth. For these vertical asymptote discontinuities at endpoints, the real question is how quick does that curve get close to that position? If it's slow, whatever slow is, it'll diverge. If it's fast, like in this example, this is fast, and we got rid of. In this example, the vertical asymptote is on the right. The curve in green gets close fast. That's why it converges. Just so you guys know, that's kind of a good fundamental thing to kind of know about in terms of these two definitions. And there's only two definitions. The left endpoint discontinuity, the right endpoint discontinuity. Sometimes you'll have a finite answer. Sometimes it'll be infinite. It's all really, does it get close fast enough? To the, actually, it's studied in more advanced calculus courses. Because that's a good question. See, the thing about some of these things, that it is studied. Like, what does fast enough mean? But it's not studied here. In fact, you get to take, if you major in math, you get to take calculus all over again. You go, really? This time you have to prove it. But you have to do, you got to learn about the art of proof first. And then you start to prove some of these things. And then you'll start to look at some of those details. But yeah, the people do study that. It is there. It's very fascinating. But for us, in all honesty, that's as far as it goes. And then, I have my... Let's do something like this first. I don't want to kill people off the bat. You see this, you go, oh my God. Okay. Question like this. You go, Mr. Judge, how do I handle this? Oh, yeah, how do I handle this situation? Okay, we'll talk about it. This is actually the third case, I think. Go to the denominator here. What do you guys know about this denominator, by the way? See this denominator? Yeah. You go, okay, where's my vertical asymptote? Oh, 2x is 3. Oh, you know what that means? X is 3 halves. So 3 halves is 1.5, by the way. Okay? What do you guys know about your interval? 0 to what? 2. So this is actually the third situation. You say, what do I do if I have the vertical asymptote right in the middle? Yeah, unfortunately, you have to break this up. Break it up from 0 to 3 halves. X minus 3. 2x minus 3. And add it to this integral. So the point I want to make now for you guys is this. Hopefully you observe this here. You got 1, you got what? 2 improper integrals now. The problem is at 3 halves, you have a vertical asymptote, okay? So there's a vertical asymptote at 3 halves. So in order to have convergence to a finite number, what do you guys think you have to have? Convergence for both. They both have to be finite. So if the first improper integral is finite, the second must be finite, and then the sum is finite. Yes?
So essentially, for
Yeah. Yeah. So like, for example, this first improper integral, write down the interval here, right? You have 0 to what? 3/2. And now you have the what? Right endpoint discontinuity. And then this is from 3/2 to what? 2. Here you have the what? Left endpoint discontinuity. So you might want to write that down. Say, okay, this is a right endpoint. Discontinuity. The other is a what? Left endpoint what? Discontinuity. So, you say, oh, okay. You're going to go really from 0 to t here. Is that right? You're going to go from t to what? 2 here. So you might say, what do I do? Well, what do you do when you have a right? Where is that? Oh, there we go. Case number, I call it case 1. You have a right endpoint discontinuity. You're going to go to the discontinuity from what direction? From the left. So it's like backwards. You guys know what I'm saying? A right discontinuity approaches that discontinuity from the left as, what is this? A left discontinuity approaches that discontinuity from the what? From the right. So maybe you can remember it that way. It's backwards. Right discontinuity, approach it from the left. Left endpoint discontinuity, approach it from the right. And use your definitions now. You say, okay, what's my definition? Go back. Say, what does that become? So for this integral, you say, okay, that's the limit as t goes to 3/2 from the left, 0 to t, x minus 3, 2x minus 3 dx. Plus, this is the second one. Limit t goes to what? 3/2 from the right, because you have a what? Left endpoint discontinuity now. And so we're going to integrate here. I guess we have to put it over here. Okay, now you go from 2 to what? 2 to t. X minus 3 to x minus 3 dx. So there's going to be 2 improper integrals when you have that discontinuity. The vertical asymptote somewhere in the interval. So, of course, they're going to give you a whole bunch of questions to warm up and practice. Left endpoint discontinuity, right endpoint discontinuity, and then they'll throw the discontinuity somewhere in the interval. But that's kind of how you do that. Now, remember in purple here, what is this going to be in purple? You need that I of t. Okay? So, try that out. You go, okay, my I of t is really going to be now, in this case, your limits will change. Okay, so be careful with that. Now, does anybody happen to know how do you handle this situation? Yeah, how do you integrate this? Man. Huh? You guys know? What can I do? Yeah, I want you guys to note something here. I don't know if I did this for you guys. Let's note. You know how it's 1 and 1? I mean, I can write it this way. I can say, oh, isn't that x over 2x minus 3 minus what? 3 over 2x minus 3? Now, the one on the right is easy to do. It's the one on the left that's not so easy to do. Okay, now here's another idea. Has anybody finished with the partial fraction decomposition homework? Say yes. Okay, good. So, in that homework, you might have seen there's some examples there. Do you guys remember doing long division from beginning algebra? Anybody ever do long division from beginning algebra? You take this term here. Let's see if I could get this out. X divided by 2x. Remember this? That gives you 1/2. That's a constant. You put it up here. Now 1/2 times 2x minus 3 is going to be x minus what? 3/2. Now subtract. Oh, really add. Change the sign. Now 3/2 is going to really become multiply the bottom by 2 and the top by 2, right? So it's negative 6/2 plus 3/2, which gives you negative 3/2. Turns out you're done. Are you guys done? I think you're done. So this is called, by the way, if I try to get some colors out, quotient remainder. And then in blue, this is what you're dividing by. Not blue. Let's change the color pink. This is a mixed number. Quotient, remainder, divisor. So this fraction equals quotient, remainder, divisor. This fraction equals 1/2 minus 3/2 over that 2x minus 3. So the fraction becomes 1/2 minus 3 over 2, 2x minus 3. We can integrate this instead. So that fraction we have here is equal to this just by doing some long division. And then now you say, what is this? Well, if I have to integrate, yes, I know I have some limits, but, you know, I can actually get my answers quick here, and I'll put the limits. How do you integrate this down here? U sub. U is 2x minus 3. Is that right? So by U sub, you guys know you get what? 1/2 natural log absolute value 2x minus 3, which will be 1/2 x minus 3/4 natural log absolute value 2x minus 3. What were my limits again? My limits were what? 0 to t. All right. So we get what? 1/2 t minus 3/4 natural log absolute value 2t minus 3 minus 1/2 times 0 minus 3/4 natural log 2 times 0 times a negative 3. 1/2 t minus 3/4 natural log absolute value 2t minus 3. Now that's minus 0. That's going to be plus. I think it's plus 3/4 natural log of 3. Okay, you guys okay with that one? Anyway. So this is my I of t. I wish I would have kept it in purple. Okay, what are you supposed to do with this? Take the limit. What's the limit? I think that was the first one, right? T goes to what? T goes to 3/2 from the left. So you're going to say this. So, okay, let's get that red. As t goes to Is it 3/2 from the left? So what do you really, these terms here are constants, right? So they're finite numbers. What you really need to know is, where does this go to? So I'm going to say natural log 2t minus 3 goes to what? Do you guys know? Where does this... So I think you have to focus first on what? Right? So we're going to have to say 2t minus 3. Where does this go to? As t goes to 3/2 from the left. Where do you guys think that goes to? T is going to 3/2 from the left. Where does 2t minus 3 go to? Zero from the left? Okay, well, it doesn't really matter if it's 0 from the left or right. You guys know why? Because now you take the absolute value, that's going to 0. Is that true? So where does this go to? If my inside function is going to 0, what do you guys know about that? Where's that going? I don't know. That's going somewhere. What do you think? It's not a double-sided limit. Say it doesn't matter. Where is that going to? Anybody know anything about the natural log? How does that natural log curve look? Curves every B student should know. You guys know what I'm saying? So if what's inside that domain, it doesn't matter. This thing's going to 0. Is that right? The inside's going to 0. It's not equal to 0, but it's going to 0. So what would you guys say as you go to 0 here? Let's go to 1. Where's that going? Is it going to negative infinity? So what does that mean? What do you guys think that means? It doesn't matter that this is a constant and this is a constant. This is still going where? Yes. So I of t goes to what? Negative infinity? Now, what does that mean? Because this means a lot, ladies and gentlemen. You know what this means? That this first improper integral, what? Diverges. So if the first diverges, it really doesn't matter what the second one does. So that means this whole thing, what? Diverges. It won't matter. So in other words, in order to get convergence, you need convergence for what? For both of those integrals, not one. For both. And then also, let's take a look. Some of these are in the homework, I guess. So to 4, 1 over what? x squared plus x minus 6 dx here. And remember, we got to know where this function, where the vertical asymptotes are. The integral is from 0 to 4. So you might say vertical asymptotes, don't you have to factor, I guess, right? I think that's x plus 3, x minus 2. Is that true? Okay. So you guys know what that means here. We're going to say what? This means what? X plus 3 is 0. It means x minus 2 is 0. Is that right? And then what does this mean? X is negative 3 and x is 2. What's the deal with this? What do you guys think? What's the story now? What does this mean? Well, negative 3 does have a vertical asymptote, but it does not matter, right? X is 2 does matter because it's in the interval. So again, unfortunately, we have to integrate from 0 to 2 dx. So the discontinuity is at 2. Yeah, that vertical asymptote at 2. So you're going to have to split that up along the vertical asymptote. Now, again, for me, let me move it down or move it around. See if I can remove it. I would say for this first one, look at the interval, right? 0 to 2. Here, 2 to 4. You got a discontinuity at 2. You got a discontinuity at 2. What do you guys know about this one here? What do we say? You have a right what? Endpoint discontinuity. And then over here, you have a left endpoint discontinuity. Okay, so remember, it's the same thing. You want to integrate one. Actually, here's the deal. It doesn't matter where you start. Integrate one. You want convergence. If you get convergence, you go to the next one. If the next one converges, well, good, then you have convergence. But if you start and you get divergence, well, then you can stop. So as you guys know, you say, which one should I start with? I'll start with the first one, right? A right endpoint. Okay. And let me get this here. Let's get this here. So we start with the first one, and I don't know, you can call that sometimes you call that I1 and I2. Improper integral 1 is the integral from what? 0 to what? 2. 1 over x plus 3. You guys know why I left it this way? Maybe you have a hint. And I would still highlight that 2, and you get what? Right endpoint? Okay, limit from the left. T goes to 2 from the left. 0 to t. And this is your what? I of t. Yes, you guys have to use what? PFD. Okay, so now you might say, okay, how does that look? I'm going to say 1 over here. X plus 3, x minus 2 will be A. X plus 3, B, what? X minus 2. Now, I'm going to let you guys know, I know what A and B are. A is negative 1/5. B is positive 1/5. Okay, using PFD. So I'm a little bit superstitious, so I put the positive term first and then the negative term. I just think it makes my arithmetic easier. 1/5 x minus 2 minus 1/5 x plus 3. Now, that means I'm really integrating 0 to t. 1/5 x minus 2 minus that 1/5 x plus 3, and that's dx. Okay, so you're going to get this 1/5. You're going to integrate 0 to t x minus 2 dx. 1/5 integral 0 to t x plus 3 dx. 1/5 natural log absolute value x minus 2 minus 1/5 natural log absolute value x plus 3 here, which is 1/5 natural log absolute value x minus 2 over x plus 3. And you evaluate that from 0 to t. Now I'm going to go back to purple because that's my I of t, so I should have been purple all along, right? And that's I1, by the way. Okay? So I1, I of t, is if I plug this in, it's 1/5 natural log absolute value t minus 2, t plus 3, minus 1/5 natural log absolute value, really, of negative 2/3, which is positive 2/3. Okay. Get rid of that. And then you say, what am I supposed to do with this? Well, what is t supposed to go to? Remember this? T is supposed to go to what? Oh, here we go. 2 from the left. So t goes from 2 from the left. We need to know, what does that I1, which equals I2, where does that go to? That's really the limit. T goes to 2 from the left, 1/5 natural log. T minus 2, t plus 3 minus 1/5 natural log of 2/3. All right. Did I screw up on it? It's absolute value. So what happens is you put the 0 there, and you get negative 2/3. So it's absolute value of negative 2/3, which will be the positive 2/3. And again, this limit is really going to be what determines the limit is this port. That's what's going to, because the other values are finite values, just so you guys know. So you're really just going to be concerned now with this. And then again, I mean, I want you guys to just note what I'm saying here. That t is going to 2 from the left. We need to know what the natural log absolute value of t minus 2 over t plus 3. Where does this go to? Because if we know, if that's finite, all the other values are finite. So use properties of limits to get that finite limit. It doesn't matter what the value is if they're just asking convergence or divergence. If that's infinity or minus infinity, then then it diverges. So that's really the mechanism or the control, what's happening with that limit. But before that, you might say, well, I got to know where really the absolute value goes. In all honesty. Because this is a limit question, we have to say, where is this going to? Well, it's going to be positive, is that right? Because you have absolute value. So where does that really go to again? I think that goes to, by the way, that's nice and continuous. This is like the absolute value of 0, is that right? So you go absolute value 0. This goes to 0, so you guys know. Then what does the natural log of that go to? Yeah, as you approach 0, where are you going again? Negative infinity. The point is, this means that you have a what? Divergent situation here. So this I of t goes to negative infinity. So it diverges. So that first improper integral diverges. Where is it at? Let me find it here. It's right over here. So the second we find that this thing diverges, we don't even have to do the other one. This thing diverges. So you want to show your work, But that's kind of an interesting, very interesting kind of question here. Try to see some more. Okay. How about something like this? This is kind of a nice, simple question. Okay. And what do I mean? What do you guys know about this denominator? X can't be 0. So you have a vertical asymptote at x is 0. Is that right? So what's the interval? 0 to 3. What does this mean, ladies and gentlemen? You have a vertical asymptote where? Left endpoint. Discontinuity. So by definition, this is the limit now as t goes to 0 from the what? From the right. Remember, it's backwards? Left endpoint gives you a right-handed limit. So remember, the problem is where? At 0. So you're now going to integrate from what? T to 3. There you go. I of t is t3 1 over, isn't this really x to the 3 halves, by the way? Is that true? So that makes this integral a lot easier to do. You say, what do you mean? That's x to the minus 3 halves. Okay. All right. So what does that give you? If I add 1, what is this? Negative 1/2 divided by negative 1/2. What is that going to be? Is that negative 2 over the square root of x? I think so. t, 3. So negative 2 square root of 3, and that's going to be minus a minus if you wanted to see every detail. Okay. So what happens now with this one? Do you guys know? Got to take the limit. Limit is what? G goes to 0 from the right. Okay. All right, so let's see. ST goes to 0 from the right. I of t, which is 2 square root of t minus a constant there. Where does that go to? Now, what does it mean t is going to 0 from the right? It means t is positive. And if that's getting smaller and smaller and smaller, this is the key right in here, so you guys know, right? What does that mean? That portion is going where? Let's see if you guys know. Is it positive or negative? It's positive. Is that true? So where is that point in red going to? Isn't that positive infinity? Why? The denominator is getting super, 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 super small. It's positive, so it's defined. Square root of that. It's not imaginary. But it's getting smaller, smaller, and smaller. It's in the denominator. That means the whole fraction gets what? Big. So this is going to be big. It doesn't matter if I subtract what? Any finite number. This limit is what again? Infinity. So in other words, this diverges. So this one equals, infinity. It's a divergent situation. Anyway. So if I go back, let's say this. Let's go back to the browser here and demonstrate and remind you guys